Hi everybody, welcome. Spring semester 2019 Exam 2 review for D4. I want to thank you all for being here, but especially Andrew, who gave up his time this evening to record this. So Andrew and all your colleagues at SITTV, thank you. All right, I'm excited to get started. My goal for tonight is that you leave here happy. That means you leave here confident that you think you have a great chance of knocking this test and getting like a 99. All right, so if you have any questions, please ask them. The home audience is not able to ask, so they're relying on you. My goal for tonight is to go over the most previous exam 2. These exams are posted on the Canvas course website, so these should be available. We're going to go through quiz 2 from the fall 2018. Okay, so we're looking at quiz 2, fall 2018. Now, just a heads up, we're recording on Wednesday evening. There is a little bit of Chapter 6 that we have yet to cover that's on the exam, which will be covered this Friday. So I'm actually going to show you some new material that you may not have seen yet. But we'll be covering it again in the lecture on Friday. But you'll see the problems, and I'll tell you how to solve them. And if I leave anything out, I'll fill it in on Friday. But you'll see some of the material tonight that might be new. All right. Okay. Before we see how the solution is, by the way, I should have prefaced my remarks. What does this exam cover? Sorry for not doing that first. This exam covers chapters 4, 5, and 6. Okay, so 4, 5, and 6. 4 and 5 were primarily A to D conversions, the concept of a Fourier series and a Fourier transform, and Chapter 6 was prop stats. Okay, so that's basically what this exam covers, Chapters 4, 5, and 6. So we start with problem 1, and problem 1 is a Chapter 6 problem. I say, great, how do I know that? It's prop stats. So it says, here's the deal. You're given a Gaussian random variable with a certain mean and a certain standard deviation. Determine the probability that that random variable is less than 325. So I'm hoping that this is a problem that you would feel comfortable with when we have our exam. And let me tell you how I solve it. First thing we have to do, since this is a Gaussian problem, is we have to convert everything to what's called the z variable. That's because there is a z table. And we can think of the z table as a Gaussian random variable where we subtract the mean. So the z is a Gaussian random variable with 0 mean. And we divide by the standard deviation. So we can think of z variable as Gaussian with 0 mean and a standard deviation of 1. So the first thing you should do is plug in all the numbers. Now, be careful. What's x? X is what we're determining we're either greater than or less than. Here it's less than. So x is 325. In the problem statement, I gave you the mean, and I gave you the standard deviation. And we now get z is minus 2.10. So what we're now going to say is the probability of x being less than 325 is the same probability of z being less than minus 2.10. Now, I don't know about you, but I have to draw this. Once I draw it, I see it, I got it. All right? So I just do a quick sketch of the Gaussian, and I say, look, what am I looking for? I'm looking for this area here of being less than minus 2.1. That area is what I want. So I say, great, how do I get that area? Well, the first thing I notice is that's the same as this area because of symmetry. Now, you might remember from our last lecture, but if you don't, it's okay because that was before spring break. You might remember that we have single-sided z-tables. So what I can get is this area here. So let's just do this once. I want the area from 0 to 2.10. So I say, okay, do you give us the z tables? Absolutely. My colleagues, I also give you formula sheets. So you can look at the formula sheet online, Justin, and it's going to be the same formula sheet. So I give you the formula sheet. This is the z table. Okay, great. So my colleagues, I want the area from 0 to z. And that in our case was what, 2.1? So just to make sure you can read these tables, and please let me know if you can't, if it doesn't make sense. Here's 2.1, and this is 2.10, and so on. So 2.10, I think, is what we wanted. So that is 0.4821. Okay? So that area is 0.4821. Hopefully I'm doing this right, my colleagues. I don't want to make a mistake with Andrew recording. Okay. So that becomes then the area of 0.4821. However, the area I want is not that, but I want the area of what's called the tail. So how do I get that? I'm hoping you know this. If not, let me know. Symmetry. The curve has an area of 1. Half the curve has an area of 0.5. So that area right there, the area of the tail, is the total area of the right-hand side minus the area that goes from 0 to 2.10. So the probability of x being less than 325 is given by this. Let me pause. Our first problem, how do we do? All right. I saw a couple of thumbs up, a couple of nodding of heads. Let's keep pushing on. I want you to stop me, though, if you have any questions. Okay. Again, a Gaussian problem, just a little more challenging. Okay, so now we have an upper and a lower bound. So I call the lower bound x1, and I call the upper bound x2. So once again, we're given a mean and a standard deviation. So now we can calculate z1 and z2. Same formula. This formula is given on the formula sheet. X minus mu divided by sigma. So I plug in what's given. Note x1 is minus 96.5, and x2 is minus 94.7. So I get values of z1 and z2. Now again, this is me. I got to draw this. I got to draw this, and I say, okay, I want this area. The area from roughly 0.42 to 0.75. Now, do you see how to do this? I'll show you, but do you see what we have to do here? Okay. I see some nodding of heads. So again, we're using a single-sided z table. So I look here and say, great. We go to the z table, and I get the area from 0 to 0.42. So my colleagues, I get this area here. So go to the z table and go down to 0.42. If I've done it right, which I think I have, I get 0.1628. Then I want the area. I get the area from 0 to 0.75. Okay? And again, go to the z table, look up 0.75, and I got that 4-digit number there, 0.2734. So now, to me, once I draw it, I can see it. I want to subtract those two, because what I want is the area that doesn't overlap. right? The non-overlapping area. I want to subtract those two numbers. So subtract the two numbers, and you get it, and you're done with part B. So Gaussian, I think these problems are okay, but I want your feedback. Do you feel confident with them? Okay. Yes, Magdalena.
For these, do you not want us to use the third decimal place in the Z table, or just round it to 2 decimal places?
Does the Z table have a third decimal place?
Yeah, it's like just not the first column. So like you can go to the 0.41 and then go to the 0.005.
Are you No, Magdalena, you could be right. Forgive me. You could be right. Magdalena is questioning about the number of decimal places. Forgive me, and I should know this off the top of my head. I thought the table that we use was only 2 decimal places.
Oh, never mind.
I'm wondering if you're thinking of maybe your prob stats table or... So it only goes out to 2 decimal places.
Yeah, I didn't see where the decimal was. Never mind.
No worries. Thank you, Magdalena. So I think that's why I did it out to only 2 decimal places. All right, I think this is what we did, right? Good. Problem 1 is done. How do we do? Onward and upward. Now, problem 2. My colleagues, problem 2, we haven't officially covered yet in class. But before I get there, how can I help? Number 1B. I know, one we just did. How can I help? Okay. My colleagues, we're about to now look at a problem that we haven't actually covered in lecture yet. So I'm going to present the formula. On Friday, I'll derive the formula, but I'm not going to ask you to derive it. I'm going to give you the formula, and let's see if tonight we can understand it and use the formula to see what's happening. We're good? Okay. My favorite part of Chapter 6 is Friday's lecture. So I'm already looking forward to Friday's lecture. Now, I recognize for many of you this is new. So here's the deal. You're going to use something called Gaussian parameter estimation. So here's the deal. I come up and I say to you, I've done a lot of measurements. You know, maybe the average transmit power for a wireless sensor. And I've measured a lot of these wireless sensors. And I think, after all my measurements, that mu is between these two numbers. I say, wait a minute, what's mu? Mu says, Matthew, does this make sense? If you and I measured every wireless sensor made by this manufacturer, we could then calculate mu. Mu is the true value. Okay? I don't know mu. How come I don't know mu? Because I haven't measured everything. I've only measured maybe 100. Okay? So what I do is I say, after I measured 100, how many actually did I measure here? 105, not bad, okay. Measured 105, I say, look, I'm going to tell you that if Matthew and I measured every wireless sensor, the real value of mu would fall between here and here. And you say, okay, that's pretty impressive. And we say, how many of them did you measure? 105, that's n. What's the standard deviation of the sample? So you have your sample, and Matthew, we're going to measure all of them. Take the standard deviation. So, boom. Now, it turns out I'm asking you this question in a very tricky way. I ask you, how confident are you that this mean here, the true mean, really falls between there and there? How confident are you? Are you 85% confident? 90% confident? So you say to yourself, okay, I need a formula. Okay? So here's what the formula says. It says the unknown mean. We're not going to measure all million sensors. The unknown mean is X bar, the sample mean. Okay? So we measured 105, we got a mean. Plus and minus, Z alpha over 2. I have to figure that out. Times the standard deviation over the square root of n. So here's the deal. I ask you, how confident are you that if we measured everything, the real mean would fall between those two numbers? To answer that question, you got to figure out Z. Now, this is where some people make a mistake right up front. I don't want you to make this mistake. See the formula? Mu is X bar plus and minus something. I don't give you X bar explicitly. I say mu is between here and here. How do I get X bar? I think I heard someone say it. It's in the middle. Perfect. Excellent. It's in the middle. If I tell you mu is X bar plus and minus something, I give you the range. What's X bar? The middle. So what I did is, we have X bar to be the middle of this interval. So my colleagues, take these two numbers, add them, and divide by 2. Or however you want to figure out the middle. So now we know that X bar is this. Am I doing okay? Now, what happens next is I say, wait a minute. I know X bar is 102.3. So, okay, that goes there. All right, 102.3 plus what gives us 103.4632. You see, that's going to be the plus and minus. All right? So what I do is I make it a little bit challenging here, but I say, look, 102.3 plus and minus this number gives us that range up on top. Let me pause. For some of you, you're seeing this the first time. How are we doing? Good. So now, Justin, what I know is I know this equals this. So I say, good. Now, I know n, 105, and I know the standard deviation, whatever it is, 8.7. So what can I solve for? Z. Now you might say, well, what the heck is Z? I'm going to get there. But now I know I can solve for Z. So I say, excellent. I can now solve for Z. And Z is the square root of n over, I just rewrote this, right? Plug in all the numbers. Okay, plug in all the numbers. I rewrote this. My right fielder, you're by yourself up there. How you doing? Doing all right. So I say, okay. I get Z is 1.37. Now let me pause. There's only one last step to go. How are you doing? Because you haven't seen this before, I don't think. How you doing? Justin. Oh, Justin.
I just have a question about the notation. So it's Z and then it's alpha divided by 2.
Yeah.
What does that mean exactly?
Yeah, Justin, I was hoping no one would ask me that because I then have to explain the notation. I'm going to get there. I'm going to see right down here. I draw something. Give me just a moment to pull that down, and I'll show you. Okay, good. Thank you, Justin. Question then. Okay.
For the notation in the formula, the symbol for standard deviation is the standard deviation of the population, right? Didn't you give us the population and the standard deviation of the sample?
Wow. I mean this sincerely. You're good. You're good. I tried to sneak something I should have known, not with this group. I tried to sneak something by, and I got caught, and I deserve to get caught. All right. Here's the question, the comment, not a question, the comment. I give you this formula, and you say, well, wait a minute. I remember from our exciting lectures that this is the standard deviation of the population because it's a Greek letter. But you don't give us the standard deviation of the population. You give us the standard deviation of the sample. So here's the deal. You're not going to like this answer. I don't know the standard deviation of the population. Why? Because if you go back to the, if you go back to the formula, you need to know the mean to calculate the standard deviation. But I don't know the mean. So I can't get the standard deviation of the population. So here's what we do. We use the standard deviation of the sample. There you go, and assume. That's it. But you were very good. I mean that. You were very good to catch that. So I do not know sigma because it's one of these life paradoxes. If I knew sigma, I would know the mean. But that's what the problem is trying to figure out. So I assume. I say that the sample is close enough and we won't tell anyone in the math department and we're okay. Did I do all right? Excellent. I had another hand. Was it Matt?
The 1.16 number, that was...
Let me scroll down, Matt. The 1.16 number. Yes.
That was just half the distance between the 101 and the 103 up when you give us mu in the statement of the question.
Yes. Help me out. I think you said it right, Matt. Can I just say it back? That's the interval on top. The middle point is 102.3. Now, 102.3 plus and minus this number gives us the lower and upper bounds. Are we saying the same thing?
Yeah.
Good. Good. Make sure I'm clear, Matt. So, thanks. All right. Now, here. Justin, you asked a great question, and let me now answer it. My colleagues, why the notation z sub alpha over 2? So here's the notation that's used by people who do Gaussian estimation. Alpha is the area under the tail, both tails. So for example, suppose we had to be 98% confident. That would mean the area from here to here has to be 0.98. So the area under the tails is 0.02. So we would call that z sub alpha over 2, 0.02 over 2. We're getting a single-sided area of the tail. So here we go. What do I know? Z alpha over 2 is 1.37 down to minus 1.37. What I want is that area. If I had that area, I got the answer. So we got to be very careful. I now go to the z table. Magdalena, I'm thinking of you here now because this is very important. Okay, we got this now. We go to the z table, 1.37. Now, Magdalena, I liked your comment before. So now, what am I looking for? The value of z is 1.37, okay? So this is 1.3. Now make sure I do this right. 0, 1, 2, 3, 4, 5, 6, 7. Right? 0.4147. Justin, what have I found? I found the area on single side of the curve from 0 to z. And it's what, 0.4147 was it? So my colleagues, what is the total area from minus to plus? Twice that. Very good. So how confident am I that if Matthew and I were to measure every wireless sensor, we would get a mean in between those two ranges, within that range, approximately 83%. Kind of low. So what do you think we would have to do? Right, measure more. Measure more, exactly. So a story in life, if you want to be more confident, you got to measure more, right? It's like my dad, who was a carpenter, said, you cut twice No, you measure, oh boy, he'd be mad at me. You measure, maybe that's why I was crazy. I used to cut twice and measure once. You're supposed to measure twice and cut once. Sorry, Dad. All right, are we good? Sir? Why do we multiply by 2 here? Because we need the total area from here to here. We have a single-sided z-table. We just got the area on one side. So we need the total area. Because the symmetry, they're the same, we multiply by 2. How did I do? Good? All right. All right. You did your first Gaussian estimation problem. All right. Well, maybe not. You might have done it before, but hopefully it makes sense. We're good? All right. Now, I have a favor to ask you. I'm already thinking ahead to the summer course. I'm running out of ways to ask this problem. So I'm on my own for your exam. But listen, if you think of a good way to come up with a killer question for the people over the summer, let me know. I'm running out of ways to ask questions like this. So, all right, here we go. The output signal of a sensor is analog. Okay. Can vary from -10 to +10. Okay. Highest frequency. Oh, so right away you know what's coming. Bet you sampling and maybe a filter. And I don't know. The highest frequency is 2500 hertz. You want to convert this to an n-bit digital signal. The digital signal should have a resolution error. Remember, the resolution error is because we have a round off, and there's a formula which I give you for that. Resolution error of plus or minus 50 microvolts. So you might say, wait a minute, what's a microvolt? It's plus or minus 50 times 10 to the -6. All right, I don't know how to ask this any differently. Draw a block diagram. Okay? Draw a block diagram, all right? And what I'm looking for, and I'm hoping you know this, this is the bare minimum I would need to see. Hopefully you're comfortable that we would not connect the sensor right to the A to D converter because there's noise. And I don't know the highest frequency in the noise. So I have to put a low-pass filter to get rid of the noise. Okay. Now, you can call it a low-pass filter, or you can charge more for the filter if you call it anti-aliasing. Okay. So call it an anti-aliasing filter. Okay. So that's it. That's part A. Determine the value of n. I say, wait a minute, what's n? N is the number of bits per sample. So now what you're doing is you're picking your A to D converter. So you want to pick a value of n. That makes sense. So we're told in the formula sheet that this is the formula for resolution. You might remember we pretty much derived it in class. The upper range minus the lower range divided by 2 to the n. N bits, I have 2 to the n levels. And remember why it's plus and minus a half? Because where's the worst place I could fall? In the middle. So I get half of the interval, either up or down. But you don't have to even know that. I give you this formula. Now, plug it in. Plus and minus a half. Now, we had a range of 10 and minus 10. So it's 10 minus a minus 10. Be careful of the double negatives. 2 to the n. That has to be less than 50 microvolts. Now, my colleagues, however you want to solve it, you can use logs. Did I use logs here? I guess I did it by trial and error. Fine. You can guess. You can also use logs. However you want to do it. So I guessed 16. My resolution error was 152 microvolts, too big. Now notice it comes down by a factor of a half, Matt. So n of 17, half of that, roughly 76, still too big. So finally, I got to 18, and I got half of that again, which is about 38. So n is 18. So I need an 18-bit A to D converter to meet the resolution requirement. Yes, my colleague? Excellent question. What is the reason I started at n equals 16? Because I knew the answer was n equals 18. I made up the problem. So I said, okay, I have to make it look convincing, which obviously I didn't. So I said, let's do n equals 16, then n equals 17. But I knew it was n equal 18. So honesty is the best policy in life, you know. So if you want to guess and check, you know, it goes up and down by factors of 2. And you can probably do a pretty good guess after your first 1 or 2. You could also do logs. Did I do all right? Okay, thanks. Please.
How would you solve it by logs?
Oh, that's assuming I can remember how to do this. Okay, help me out. Can someone, maybe with a calculator, check this out? So let's solve it for exactly equal to 50 microvolts. Okay, and I'm going to get an n as some fraction, and then I'm going to have to round up. So here, write this as 50 times 10 to the minus 6 equals plus and minus 0.5. And what is that? That's 20 over 2 to the n. Did I do this right? All right. So at this point now, I would like to get the 2 to the n by itself. All right. So I'm going to multiply both sides by 2 to the n. Now, please help me out. It's Wednesday night, and I'm tired. So I'm going to need all of you to help me out here. 0.5. And this is times 20. And I'm going to divide this by 50 times 10 to the minus 6. Does it look good so far? All right. Now, we got this plus and minus, but it is symmetric. So I can look at either the plus or the negative. I'm going to get the same answer, right? So with your permission, I'm going to drop the plus and minus and make it just plus, because I'm looking at an interval. So now we can do log to the base 2, but my calculator doesn't have log to the base 2. So I would take this as n times log to the base 10 of 2, only because I have a log to the base 10 calculator, equals log to the base 10 of all of this. Half of 20 is 10, divided by 50 times 10 to the minus 6th. Okay? So I would get, does anyone have a, I want to check it because I'm being recorded. This, they show it to the dean. I'm fired if I'm wrong. They won't know why they hired me.
I got 17.6.
All right. 17.6. Now, that means because I made the bound equal, if I chose 17, it's too big. Even if it was 17.1, it's not a rounding issue. I have to choose either 17 or 18. I always go up. So is my answer 18? Yeah. Whew, we did it. Good man. Good man. Thank you. Thank you. Thank you for the assist, everybody. All right. Now, oh, yeah. To me, this is a fun problem. It's not meant to be hard. The trick is let the units solve the problem for you. See, what's happening is we have a sensor. And Matthew, this is very, very practical. Imagine here, so many people have home security systems now with cameras. Okay? Well, suppose you're hooked up to a hard drive or some optical storage system. How much can you store? Like how many days can you store? How many hours? That's, like if I go on vacation for a week, would I have enough memory for a whole week? So it says here, determine the minimum number of bytes. Now, what's a byte? 8 bits. Determine the minimum number of bytes that will be generated in a 24-hour period. State all assumptions. So I say, okay, I think we got this. The sensor, here, the sensor has an output of 2,500 hertz. At the very minimum, I got to sample twice that. Now, you might say, that's not good enough. I'm going to sample at 2.5 times. That's why I said state all assumptions. But the absolute minimum is 2. Now, what does that give me? Samples per second. Good. Now, times 18. That's bits per sample. Oh, this is too easy. You see? It's bits per sample. Then times 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day. Now, if I follow the units, this gives me bits. But I don't want bits. Typically, computer engineers and people who work in this field measure everything in bytes. So my last conversion is I multiply by 1 over 8, which is 1 byte equals 8 bits. I calculate all this up, and I get a fairly large number. What? 972 million bytes. So you would need a storage capacity of 972 million bytes to store one 24-hour period of this. That, I think, is good to know. I mean, it's good to know how to calculate that. Let me pause. How do we do? Yes? Yes, at least. Yeah, you would have to justify it. Now, you know, now that I've said this, the way I worded the problem, I can see it's ambiguous. Determine the minimum number of bytes, but then I say make all, state all assumptions. So here's what would get you full credit. Suppose you sampled that 3 times. What we get at full credit is saying, I know I only have to sample twice, but I'm oversampling. See, then I know. Because I don't want someone to pick a random number and say that's how many samples per second I should have. But if you somehow show I could have done 2, but I chose to do 2.5 or 3, then that's perfect. Or you could have just done 2. Good, thanks. All right. So hopefully you're doing okay with this. I love your questions, by the way. Look at this. We're up to number 4. We're trugging along. Matthew, we're making great progress. All right, now, I think you know this. And if you know what I'm about to put on the board, there's no way I can trick you on this type of problem coming up. Here's what you need to know. Two sensors in parallel. Sensor 1, sensor 2. The probability of a sensor working is P. I tell you these are independent. So if one fails, it doesn't cause the other to fail. Now, what's the probability of this system working? The better question is, what's the probability of this system not working? The probability of this system not working is the top path not working. And since they're independent, we multiply, times the bottom path not working. That's the probability of not working. What's the probability of working? 1 minus that. That's it. That's it. Simple as that. Now, if I gave you 10, you got it. If I gave it 20, you got it. So the probability of this working is 1 minus p squared. Did I do that right? I'm counting on you for me not to make a mistake here. So am I doing okay? Yes? Oh, sorry. Sorry, my fault.
So 1 minus p is just like the top not working, and then this 1 minus p also the bottom not working? Okay.
Perfect. And what's nice is 2 is, you can almost see how to do it another way, but if I gave you 5 and you didn't know this trick, you'd have to figure out all ways that we could work, right? And we only need one path to work. So at least one, well, one or more. So it's much better, and you said it very, very nicely. If the sensor works with probability P, it doesn't work with 1 minus P. And now the system does not work if both the upper and lower paths don't work, which is the quantity 1 minus P squared. And how do I get it to work? It's 1 minus that. But I know you understand that because you said it beautifully. Perfect. All right. Now, that's it, my colleagues. Okay, so here. I think this is interesting. At least I think it's interesting, but, you know, I don't have a life. So I think this is just kind of fun to look at. You have n sensors in a row. Now, I tell you, each sensor works with a probability 0.99. How many sensors can I connect in a row, maximum, so that the system has a 0.67 chance of working? Now, you see what's happening here? Every time I add a sensor, I'm actually making the system less reliable. Because the only way this series system works is if all of them work. It's like the Christmas tree lights. Right? One light in a chain doesn't work, that's it. In the old ones. I'm showing my age here, Matt, I'm sorry. All right? So, how big can n be? So I say, all right, wait a minute. The probability of a sensor working. Now, my colleague, this is different because it's series. So, the probability of all n sensors working is p to the n. Right? Because each sensor works with probability p. They're independent. We can multiply it together. The probability of all of them working is p raised to the n. So the probability of the system working using independence is 0.99 to the n, to the power n. Now, we require that expression for the probability of the system working must be greater than 0.67. So again, I use logs. Here I was fortunate enough to write it out, so I can rely on this. And we get that n has to be less than or equal to 39.85, which means n must be 39. If I put 40 in here, I'm going to not satisfy that requirement. So this is a truncate. Okay? So n equals 39. How do we do? So Andrew, it's interesting. The more sensors we put in a string, the less reliable our system becomes. All right, are we good? All right, thumbs up. Okay. Now, I like this one. Because now it's the same question, except things are in parallel. Okay? So, determine the minimum number of sensors. Minimum. You see, my colleagues, if I had an infinite number of sensors in parallel, it should always work. One of them should work. So here, I don't want to buy an infinite number. I want to buy the minimum I can. But I want that to be greater than, in this case, 0.98. So I want a 98% chance that this system is going to work. Now, each sensor, this is very interesting, each sensor only has a probability of working of 0.78. That's interesting. The probability of a sensor working is 0.78. But the argument is if I put enough of them in parallel, I can get to 0.98. So I say, excellent. How do I now figure this out? My colleague here knows. This now becomes, for n sensors in parallel, what is the probability of working? So what I wrote on the board, I wrote here to remind myself, if I had two sensors, it's 1 minus the quantity, 1 minus p squared. So if I got n sensors, replace the 2 with n. So the probability of the system working is 1 minus the quantity, 1 minus p to the n. And I want this to be greater than or equal to 0.98. And what I find interesting is I only got a sensor with the probability of working of 0.78. But because I'm putting them in parallel, redundancies go to work. I only need one to work. So once again, did I use logs? We solve. Yeah, I use logs. So solving here, and this is all worked out. Sorry, I guess the copier I wrote too far. You can figure it out. It's just log of 0.22. Just bring that over. I get 2.58. No, now we have to interpret this correctly. I need at least 2.58 sensors for this to work. Sensors are purchased in integers, so it becomes 3. My colleague.
Since the question does not say find the minimum number of it.
It does. It better. It better, or the professor loses some points. Ding, 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 ding. Determine the minimum number. If I didn't have this word here, you could have written down infinity. And I would have to give you full credit. So I try to be careful about those. I don't want to give away points by someone catching my English. So it's minimum number. All right, now, I guess I was in a sensor kind of mood. I gave you a part C here. Now, wait a minute, my colleagues. Okay, so I gave you this network. And I said, determine the probability of the system working. I think you got this. It may look crazy at what time is it? 10 o'clock on a Wednesday night, and we're hearing music close by us here. So you might think this is hard, but it isn't. The probability of the upper path not working. The quantity, 1 minus p cubed. The probability of the lower path not working. The quantity, 1 minus p squared. The probability of the system not working is the upper path and the lower path not working. So just multiply those two together. And Magdalene is nodding her head. Our box seat colleagues are all set. So what we get then, this is the probability of it not working. 1 minus that gives us the probability of it working. All right. So far we're doing okay? Please.
Go up to the answer for sign switched at the very end. I don't understand why.
It's probably because we divided by a negative number.
No, it was after that too.
Ooh, okay. Which one is it? Is it here?
Yeah, so
Yep.
where you have the 0.22n, you have it as less, you switch it to less than because that's where you divided it. And then at the final answer, you write n is greater than or equal to.
Right, because
What is
help me out. You're very observant. So you're good down to here.
Yeah.
You're good here.
Yeah.
All right, help me out. The log of a number less than 1 is a negative number.
All right.
Right? Did I get that right? Again, it's Wednesday night late. So I'm sorry. You know what it is? It's my fault because it's not shown here.
Okay.
But what I do is n, I have to take log of 0.0 divided by log of 0.22. I'm sorry that I wrote too far down. So that gives you the negative number. So that's why I have to switch the sign. Thank you. Thank you. We're good?
Yep.
Let's go on to the next one. I'm getting a lot of great questions from everyone tonight. All right, now, I give you a hard Gaussian just to see if you can do it. The problem number 1 was an easy Gaussian, the one we did at the very beginning. So now, use the baseball analogy, I throw you with the heater. All right, give them the heater. All right, I throw the heater at you. So here we go. I want to see if you can do it. You're given a Gaussian random variable x with a certain mean and a standard deviation. And now look at this. I ask you it backwards. Before I gave you x1 and x2, and I asked for the probability. What do I do now? I give you the probability, and I ask you for one of the bounds. Okay. So, determine the value of x2. Before I start, is the question, is it clear what I'm asking? Okay. All right, so what I do is I calculate z1, which is the lower bound minus the mean divided by the standard deviation. And I get minus 1.26. Now, I have to do some thinking on this problem, so I need your help here. I find the area from minus 1.26 to 0. I'll tell you why in a moment. Now, by the way, I can't do that with my z table. Magdalena, I have to use symmetry and find the area from 0 to 1.26. So I get that area to be 0.3962. So I say, okay, the area from minus 1.26 to 0 is 0.3962. Why isn't it? Why is the area 0.3962? Because the z table said so. No, do you want me to go to the z table? You sure? All right, good man. All right. You sure now? All right. Now, notice 0.3962, Justin, is bigger than 0.0884. That means x2 cannot be here. x2 cannot be here. x2 is somewhere here. That's why I had to get the area. You see, the area from here to 0 is roughly 0.4. I have a probability of 0.08, 0.09. x2 is somewhere here. So what do I know? x2 is negative. Or, excuse me, z2 is negative, to be precise. z2 is negative. x2 is not negative. I misspoke. z2 is negative. So what I have is z2 is also negative. Now, let me ask you the question I wrote. Do you see what I said? Does it make sense? My center fielder, we're good back there? The box seats? Okay. So now what I want is I know that z2 is somewhere here. So I just put a line. And now what do I want? I want this area to be 0.0884. But here's the rub. I only have a single-sided z-table. So, Matt, I have to use symmetry. And I have to be careful. What I'm solving for here is the positive value of z2. But z2 is negative. So what I find is that area. The area that shaded area, 0.0884, is the area from 0 to 1.26 minus the area from 0 to z2, absolute value. So I know this area is 0.3962. So the area from 0 to the magnitude of z2 is 0.3078. So now, let me just do this with you. 0.3078. Now, I got to be careful. Now, I'm doing the z-table here. Magdalena, I'm thinking of you here. Well, what did I say? 0.3078? Got it. So, 3078. 3078. Look at that. I picked a good number. I can't reach it, though. 0.3078. So 0.3078. Now help me out. That's 0.8, 0, 1, 2, 3, 4, 5, 6, 7. I think that's 0.87. So that means the absolute value of Z2 is 0.87. Are you with me down to here? All right. Now, here's what typically happens. Someone comes up to me during the exam and they say, I'm getting crazy results. Almost always, I can't tell them this, it's because they forget that Z2 is negative. So Z2 is negative. So what I get then is this formula here, minus 0.87 is Z2. I now solve for X2, and X2 is roughly 29.4. Interesting problem, Matt. Have we done okay? Magdalena.
Could you explain one more time why Z2 is negative?
Excellent. It's my favorite part of the problem, Magdalena. So Magdalena, we're given that the probability of being between two numbers is 0.08. Now, the lower number, 27.9, corresponds to minus 1.26. So here's what I did. If I were to get the area from here to here, it's almost 0.4. But the area between our two numbers is about 0.08. So it has to be to the left of the origin. Right? Isn't that nice? Now we know it's negative. And then the rest, I gathered you followed the rest of it. I was just that. We're good? Thank you. Matt.
Would you give us a question that is, start the lower bounds on the left side, the upper bounds on the right side of the Z0?
Say that again. Would I?
On the Z chart, the bell curve.
Right.
Would you give us one where the lower Z1 is on the left side and Z2 is on the right?
It might work out that I do that by accident if I'm not careful. That should be okay. It's just a little challenging, but you can get it. I know what I have done, Matt, which isn't your question, but I sometimes alternate between the upper and lower bounds. Like here, I didn't give you x2. So maybe I'll give you x2 and leave x1 to be the unknown. Did that do it, Matt?
Yeah.
All right. Good. Thanks. All right. Good. That's problem 5. I did this, right, Magdalena?
Yep.
I went through all of this? Okay. The binomial distribution. Here's the problem for me with the binomial distribution. There are multiple ways to solve this because I could define a success one way, you could define it a different way. And it gets, so let me see what we can do here. Let's see if this problem makes sense. I actually thought this was an interesting problem. I don't know if it was shared by the colleagues who took the exam, but I thought it was pretty interesting. Okay, you have a transmitter, and the transmitter is sending either a 1 or a 0. Now, an error can occur. If I send you a 1 and you get a 0, that's an error. If I send you a 0 and you get a 1, that's an error. So this is the part I thought was great. I loved this when I thought of this. An error-correcting code is used at the receiver. That means it can correct some errors. So here's the deal. If I send you 8 bits, and at most 1 is an error, the receiver fixes it. So I send you a group of 8 bits. Suppose one of them gets corrupted. 1, but no more than 1. The receiver can fix it. So the probability of a binary digit or a bit being received in error is 0.01. Using the binomial distribution, determine the probability the 8-bit block is received incorrectly. I love this. Now, how's the only way it can be received incorrectly? If there's more than 1 error. If there's 0 errors or 1 errors, the block is good. The 8 bits are good. It's only if I have 2 up to 8 errors, then I'm wrong. So here's how I solved it. There's more than one way to solve this problem. My approach, determine the probability of the block being received correctly. Now, why did I do this? I'm thinking of my colleague here who asked about the independence before. I'm thinking of you here. The block of bits can be received incorrectly if 2 bits are wrong, 3 bits are wrong, 4, 5, 6, 7, 8. That's a lot of calculating. What's the probability of it being received correctly? 0 errors or 1 error. So I figure out the probability of it being received correctly. So that's 8 choose 0, 0 errors, 8 bits correct, plus 8 choose 1, 1 error, 0.99, the probability of being right, 7 of those. So I calculate that, and if I've done it right, I get 0.9973. That's the probability of the block being received correctly. What's the probability of it not being received correctly? 1 minus. That's the answer. Binomial problem done. A hush has fallen over the audience. Magdalena.
Are we given the entries R formula and the formula?
Yes. Yes. Magdalena, if I peek ahead just again to show you. There it is there. And the formula sheets are posted along with these exams. Okay, we're good? I think we're coming down the home stretch. All right. Now, my colleagues, our second parameter estimation example. Only one thing you have to know, and I'll describe this more in the lecture on Friday. Matt, when you and I went to measure the wireless sensors in problem 2, I think it was, we measured 105. That's enough to say it's Gaussian. If I don't measure enough, it's not Gaussian. It's another distribution called student t. So I have to use a different table. The magic number, and I'll discuss why in class on Friday, is 30. So if I measure more than 30, I use the Gaussian table. If I measure less than 30 of something, I use something called the student t distribution. So notice, and Justin, I'm thinking of you here, this is the same formula, but here we use S. This is the same formula, except instead of Z alpha over 2, it's T alpha over 2 to remind us it's a different table we have to use. So we're given that the sample mean is 38.7, and I tell you the confidence level is 99%. We measure 18. What's important about 18? Less than 30. And the standard deviation of the sample is 2.9. Determine the estimate of the population mean. That means I want to calculate mu. That's the population mean, Matt, which we're not going to measure everything in the world to figure out. So I know x bar, given. I know s, and I know the square root of n. I just got to figure out t sub alpha over 2. And just in the alpha over 2 is the same meaning again. So I now come here and say, great. Now, I know I'm throwing a lot of you at this, might seeing it for the first time. You'll see it again Friday. If I'm 99 here, let me just draw this over here. And Justin, this is now, I think, a better answer to your question, which was wonderful, about the notation before. Here, it turns out student t looks a little bit like Gaussian. Okay? So here, we want to pick t alpha over 2 so that this area is what, 0.99 or 0.98? 0.99. We want this area to be 0.99. All right, now help me out. What's the area of the tails? 0.01. Right? Now, we're going to use a single-sided table. So help me out. I don't want to make a mistake. 0.01 divided by 2, 0.005. So we need to look in the table for 0.005. That's how we get it. Now, we're going to look at the student t table, and we're going to look in the column that's 0.005. Now, last thing, student t has what's called degrees of freedom. Degrees of freedom is n minus 1. So we measured 18. We have to look up the 17th row in the table. So degrees of freedom is used to parameterize the to set up the student t table. And so we get 18 minus 1 is 17. So now I go to the student t table. Okay? Now, what I do, the alpha is on the top. Now, what was my alpha? 0.005. That's here. I go down to degrees of freedom. This is not n, it's degrees of freedom. I go down to 17. This looks crooked. It's not me, right? Whew. All right. 2.898. Okay. 2.898. You plug it in and you get this or this. You can write the answer either way. So Matt, this says, given that you and I have made, what, 18 measurements? We're saying we're 99% confident that, Matt, if you and I measured every single one, the average would fall between here and here. Now, Matt, as you said before, that's kind of a big range. How do I narrow it down? Increase n. Just measure more. How do we do? Excellent. If I go above 30, we go to the Z table. Now, wouldn't it be nice if there was like a part B to this problem that anticipated that? All right. Oh, Matt, look at the sly devil that I am. I say, oops, my colleagues, I made a mistake. Did I say we measured 18 times? Oh, no, we measured 81 times. Oh, there was a typo. So now what's big about 81? Greater than 30. So, Matt, what do? Same thing, different table. Okay, so here, everything is the same except n is now 81, which means I got to go to a different table. So this is this here. So Magdalena, Justin, Matt, everyone here tonight. I now have to pick minus and plus Z alpha over 2 to get 0.99. That means, how much do I want this area to be? 0.99 divided by 2, which is 0.495. So now I go to the Z table, and I want 0.495. Do I have it? Ah. Here. What do I want? 0.495? 0.4949? 0.4951? Falls right in the middle. Isn't that beautiful? Okay, so what's the value here? Make sure I read this right. 2.5, 0, 1, 2, 3, 4, 5, 6, 7. So is this 2.575? 2.575. Now, my colleagues, Magdalena, I'm thinking of your comment earlier now about the decimal places. My colleagues, you do not have to extrapolate. All right? This was easy. It was a gimme. It was for free. It fell right in the middle. Then you do it. But if it doesn't fall in the middle, pick the closest. You do not have to extrapolate unless it's obvious. Okay? So did I measure that right? $2.575, is that what I said, my colleagues? And now you plug in, and you got it. We have one more quick problem to do. You're great to stay with me. Did we do okay on all of this?
So just for clarification, the T tables are two-sided
No, I beg your pardon. The T-tables are one-sided also. Because if you remember, Matt, help me out. I had to look up the tail on just one side. Did I want me to show you that again, or you're good? Thanks, Matt. All right. Matt, just for the fun of it, just to follow up here, help me out. This is what, 37.8 roughly, or let's call it 37.9. And what's the other one, 39.5? Let's compare that to the other interval. You see? 36.7, 40, see? Right, exactly. So when we measured 18, we had a bigger interval. When we measured 81, so it all makes sense. All right, lastly, and I know you love these problems, which is why I give them to you. It's out of love. A series of short answer questions. Ta-da-da! Okay? So, you're given a non-sinusoidal periodic signal with a frequency f. Now, this we discussed in class. I told you this was coming. I love this question. At what frequencies would we expect to maybe find energy? At the fundamental, the second harmonic, the third harmonic, the fourth harmonic? Now, if it's an odd or even function, Magdalena, I might not have it at those odd or even frequencies, but I'm going to find it at f or 2f, not at 1.73f. Next, when is the Fourier transform used and not the Fourier series? Come on, that's easy. Fourier transform is for non-periodic. Fourier series is for periodic. In our lecture, we discussed an important observation on the Fourier transform. What was this observation? Let the period go to infinity. That pushes all the other cycles out, all the other, not cycles, all the other periods, other cycles. That's right, isn't it? I'm start searching for a word here. Here. A picture's worth a couple of thousand words, especially this hour of the night. My colleagues, I'm hoping you remember this. This was, let's say, T1. And there was another one here, another one here, another one here, another one here. Periodic signal, right? So what I do is this is the period capital T. What I do is I can get a Fourier series for a periodic signal. Now, let capital T go to infinity. What happens to everything but the middle pulse? Gets pushed away. Okay? So how do I get the Fourier transform from the Fourier series? Let the period approach infinity. Coming down the home stretch. List the 3 mobile software platforms we discussed in class. I guess I'd have to change the question now to 2 because we didn't discuss Microsoft. We discussed Apple, iOS, and Android. Okay. The addition of a large number of random variables may result in a random variable with a Gaussian distribution if it's large enough. What condition must be true for the addition of a large number of random variables to result in a random variable with a Gaussian distribution? God bless. D. Oh, that went over really well. I struck out on that one. I can tell Magdalena I didn't emphasize that in class. Independent and identically distributed. Remember my trip to the science fair and the dropping of the marbles into the pegboard? Each marble was humanly, as best we can, identical to the one before it, and each experiment was repeated the same way, so it was an independence of dropping off between the pegs, so IID. All right, I like question F. I really do. Let me know if you can get it. Come on. This, I think, is the last one, or next to last one, or next to the last one. Oh, my legs. All right. If the confidence level is to be increased, what will happen to the confidence interval? If you want to go from 80 to 90% confident, what happens to the interval? It increases. Remember the story I said, if you told me your life depends upon telling me a high temperature in Hoboken tomorrow, I would say 52 degrees plus or minus 500. I'm essentially either going to be dead or right. Not both. All right, it will also increase. Why? The more certain of falling in an interval, the interval, to be more certain, you have to be the interval should be larger. G, what will happen to the confidence interval? Oh, Matt, this is just right down the home plate for you, Matt. What will happen to the confidence interval if the size of the sample is decreased and the confidence level remains the same? So now I take less measurements. The interval has to get bigger. I'm more uncertain. Confidence level will increase. Why? We are taking less samples, so we need a larger confidence interval. That's it. How do we do? What a way to spend a Wednesday night, huh? Give me some feedback. Was this helpful? All right, good. Thank you, everyone, for showing up. Home audience, thank you. Andrew, you the man. Thank you, Andrew. Good night, everybody.